So I am going to give you another short overview on what I call the crash course in inorganic and the metal complex. And this is a essential repetition of the series, and this is a 002 series and part A. And part A, I'm going to more focus on nomenclature and the isomer cases. And the d orbital energy splitting will be discussed in the part B, and along with the other isomer topics again discussing. So let me focus clearly on the meaning of the ligand. So the metal complex in inorganic chemistry, there's a metal in the center, and the ligand is essentially connected to it. So there's a metal and the ligand, and the ligand has usually lone pairs. They're trying to essentially stabilize and form the complex by coordination, bonding coordination complex, and usually N plus. So that's the sort of the one. And how many ligands do you attach to it? And one of the magic number is 6, and 6 is they form the hexa, like a hexa, and that means actually they form the octahedral structures for them. So let me talk to you about the ligands. Okay, so this is a slide that I kind of blow it up from. Okay, I don't know if it will go away. Okay, good. Okay, so this is a slide that I have I made a copy so that you guys can see it clearly, and you can see that some of the one has actually more than one lone pair electron they can donate. So this is what is called a carbonate ion, COO minus, and then there are two of them. So there's a two carbonate ion. They have two lone pairs. They can form the coordination. Ethylene diamine is one that amine. There are two of them. They can also form the coordination. This is what is called the EDTA. It's a long name. Even everyone just call it EDTA because of this unique nature about 4 arms. It's almost like a 4 arms, and they can have 4 lone pairs form the coordination complex, and this is what we call EDTA. Okay, so oxalate ion, which is from the oxalic acid, and to me it is a 2 coordination. And the ethylene diamine, which is going to show a lot, and you want to know what EN means, that's the one, and this is a coordination number 2, and the EDTA is a coordination number 4. So just wanted to recap the EN means you have a nitrogen bridged by this CH2CH bonding, and then that's a 2 lone pairs that you can see that. And so that's ethylene. Ethylene means CH2CH2 diamine, right? You have a two amines, right? So you have a 2 amine. So that's ethylene diamine, and that shows up quite a lot in this example throughout. And in talking about the nomenclature, the ligand has its name, and there are 2 classes of ligand. One is an anion, which is a negative charge one. The other one is a neutral. Okay, and there's a common theme that the negative ion, the ligand, which is for example, we call this as a bromide, chloride, hydroxide, and cyanide, for example. And this one, when they use as a ligand, they ended up having this O. Okay. Bromo, chloro, hydroxyl, and cyano. Okay? Even the oxalate ion that you see here is a -2 because there are -2 charges there, and that's an oxalato. So the O is at the end for something that ligand that is negatively charged when they are used in the nomenclature. And when you see the one with the neutral, so this one do not have any charges, and it has its own unique name. Okay, so this is just IUPAC, International Union of Pure and Applied Chemistry, the nomenclature division, they decide to just agree. So aqua and ammonia, which is we call imini. And then the CO, carbon monoxide, we call this carbonyl. And then ethylenediamine, they're using the symbol En because it's so much used. And then this is ethylenediamine is the full name. One thing that is funny is, I want to switch the colors because I know the issues already. This is the EDTA, right? EDTA is a compound name, and the EDTA is a 4-, so therefore it should have a O at the end as an anion ligand. And I don't know why the authors put this one in here. It should go up there as an anion-based ligand. And I am going to actually solve this once more, the problem solving this nomenclature. So let's do this one. So this is a compound that you see, cobalt with a En means ethylenediamine and the chloro. So this one you can start to see, okay. So then I am going to say that means a diethylene diamine. So that's the one component. And then the second component is dichloro. Okay, so I'm done with those two. And then let's look at the other components here. So other component is, this is what is called a bromide. And this one has a negative charges. So therefore, the whole thing must have a +2 charges, +1 charges, right? And the chlorine itself is give you a minus charges. So there's the total charges -2 here. And this is a neutral. And therefore, what's the charge for the cobalt? That must be +3 to make up the total charge of complexes 1. So that's therefore, you're going to say cobalt with the +3 charges. So that's one of the component that, so you got this ingredient, and then this is a bromide. So what's my answer for the nomenclature on this? And I write it in here. And then I need to put the ligand first, and the alphabetical ordering. C comes before the E. The di doesn't count. Okay, it's just coming from the name. Actually, people do not put a parenthesis for the chloro, so just say dichloro. And therefore, I need to move this one to chloro like this. Okay, so it's a dichloro. Ethylenediamine is a big, so they put a parenthesis. So the C comes first, so dichloro, ethylene, diamine, cobalt. 3. Okay, so it came a long way, and something that and then you put a space there, and then bromide. And that's the full name for this compound that you see down here. Okay, so I'm going to talk about the down here as a cobalt with a 2 ethylenediamine and then dichloro. So this is a compound that the name is shown up there. So this is an example about nomenclature, and then I'm going to move on to the something called what we call the geometric isomer. And the geometric isomers, the most common one is cis and trans. It's almost like a cis and trans is what is used in the even organic chemistry. The cis and trans isomer is we talked about it. And for the case of the inorganic compound, they can have a geometric isomer. They can also call the cis and the trans. Trans is on opposite side, right? And also there is something called a chiral and optical mirror image isomers. Chiral isomers, optical isomers, mirror image isomers. Also, there's a student who asked me about enantiomer. It's the same meaning. Okay, enantiomer. And this is all the same meaning as something that has an optical activity, although they have a same essentially bonding point. So this is to me I think that I explained it in the Chem 1 class. It's almost like a left hand and the right hand molecule. Okay. Right hand. If you try to put your gloves on the left-handed glove to your right hand, it doesn't fit. So there are different molecules. Left hand and the right hand molecule is not the same. They are sort of like a mirror images, right? So therefore, you can see that. Enantiomer. It's a mouthful name. Okay, enantiomer. Okay, well, I'll just make sure. Enantiomers. This is another name for the optical isomers. Okay, so the first example is coming from this, and this is because of the metal complexes. You have to know this notation, what this really means. And this is an ethylene diamine. It looks like this molecule with this two ligands, right? And the chlorine is just nothing but you have this. They can have this one coordination. So what that means is one EN means a two coordination. There are two of them, and chlorine is a one coordination, and there are two of them. And if you add them together, there are 6 coordination. Okay? So number of coordination by the ligand is 6, and you have a 6. 6 means always octahedral. Okay, octahedral. Aphases. Okay, octahedral. And okay, so this is then I'm going to draw the octahedral one more time using this diagram. So I'm drawing a piece of paper like here, and then there's things going up and things going up down. And I'm going to draw the one more time. There's things going up, things coming down. Okay, so this is a case where I just draw the octahedral. I'll give you an example of another octahedral, the symmetry of the octahedral. Let me draw this line. Okay, can you guys imagine this line and the other line? They form another planar structures, and then this one is going through the axis. So therefore, this one is very symmetric, and that's the way how it looks like. And then what's located in here is a cobalt. Okay, cobalt is in the middle. They're at the center, and we just have to figure out the EN and the chlorine. So I'm going to focus more on myself to the chlorine here, because the chlorine 2 is, and then I can put the rest of them here. So chlorine, if I put the chlorine here, so I'm going to pick something that is different. So chlorine here and the chlorine here, they're on the what is called a cis, the same side. Whereas if you put the chlorine here and chlorine here, they are the trans side, or the opposite side. Okay, so as the same reason that I'm going to choose something more exotic example. Okay, so how about putting chlorine here and the chlorine here? Are they the opposite side? The answer is yes. So this is another example of what is called the opposite side of molecule, the trans isomers, and whereas this one is a cis isomer. So I mean I can put, for example, here. So I can put the chlorine here, chlorine there, chlorine here, anywhere. I can put chlorine in any 4 places. They are right angled to each other. So these two are neighboring, so this is a cis. If I put this one at the opposite side, there will be a trans. So this is let me put it this other one. Okay. If I put it here, I'm still making this answer is the same. It's a cis. Okay. And then I'm going to finish up the rest of them by saying that, okay, so I need a coordination complexes. Oh, this is too close, so it's kind of causing the confusion. So let me say this is a cis. And so I'm going to finish up the, okay, there's a coordination complexes by these two. And then how about the nitrogen coordination complex by these two? This is what is called the quote-unquote EN, right? So nitrogen has these lone pair electrons. And whereas this one, you need the nitrogen forming the complexes, forming the bridges, and they give a lone pair electrons to the center metal. So this is how this looks like. Okay. So, and then what they are going to say, I'm going to highlight once more, it's easier to keep track of something that is simple, which is a chlorine, and what is the opposite side or not. And if you're looking at, this is actually probably more conventional way how people write the trends. It's a more look like more symmetric. It's the same structure. If you have, you see the plane here with like a pinkish plane. If you kind of rotate it up, you will see the same as up there. And this, let me start with the trends. This is a different way than I start explaining it in the previous classes. If I put a mirror here, think about putting a mirror. And you will see that this molecule has a mirror images. Is this mirror images is a superimposable? They are the same essentially. That's the thing. And the answer is they are the same. If you do that, the projection of the mirror and this molecule is a superimposable. So therefore, trans, optical, isomer, they cannot have one. Okay, but if you go to your class slide, and this is your class slide that I find out, and this is a case of where this is an octahedral compound, cobalt, and with a 2 En and 2-dichloro complex. This is a cis complex. This complex is you're putting a mirror, and this is a mirror images. And once you have these mirror images, you bring it down. You see that the connection or connectivity of En is kind of cross, whereas this one is more separate. So this is non-superimposable. Okay. So what that means is the mirror images and the original one, these two are essentially different, just like a left hand and right hand side. And so therefore we call this as an optical isomer, and sometimes people call chiral isomer, enantiomer, and so they are the isomers. So these are the chiral, the enantiomer pairs, and it's the same thing. Okay, so in a nutshell, that is, I think that this is an optical isomer possible. So therefore, only the exception of cis metal complex with this ethylene diamine, two of them, and then let's say chlorine dichloro. This complex, this is an optical isomer is possible. So I think that you should remember in a way for the sake of the preparing the exam. That's a good thing for you to know. When you only for the cis geometric isomer, they can have two different versions of optical isomers for the cis geometric isomers. And I also have this another slide that I have copied. If you pay close attention to these images, now you can see that if I just assume this is a cobalt 3+, then it is a cobalt with an En3, right? Ethylene diamine, there are three of them. Let me just say the 3+. And so this is a complex, and effective number of coordination is 2 from the ethylene diamine, there are 3 of them. 6 coordination, that means an octahedral, just like that. You guys have seen this one, drawn many times. This is an octahedral like structures, and then this can be connected this way, they can be connected that way, and this can be connected this way. Right? So there are 3 connections, and they show actually here, if you kind of look carefully, this is a mirror images, right? These are the mirror images together. And if you have these mirror images and bring it down and essentially rotate a little bit, just like a rotation, and you'll see that this axial position to the planar equatorial position, they are not the same connectivity, right? So this is not superimposable. They are different. So what that means is, in a simple sense, it's a metal with 3 ethylene diamine, okay, and that that can also, the example of, they can have optical isomers. Isomer, possible. This is an optical isomer. Okay, so here I give you an example where the ethylene diamine is involved, and then I use a class slide, something that for the case. And this is actually exactly the same problem, problem number 2 in the discussion problem, if you go back and use look at that. And let me continue to give more explanation about this, cis and trans versus, there's another called FAC and the MER. So FAC is a phases, and MER actually come from the meridian, which is going through the pole. And so this is when you have actually 3 identical ligand. When you have 2 identical ligand, it's much easier. Okay, 2 are there in the opposite side, that's a trans. Are they in the similar size, neighbors, close to each other, and we call that a cis. Whereas when you have a 3 ligand, and then I'm going to explain that a little bit later. So for the case of the, these are all geometric isomers, and this is all, both of them are cis trans. And cis trans, the first example coming from what is called the compound looks like that. You have a metal with a 4 coordination. That 4 coordination is actually has to form square planar. When they form the square planar, it looks like this. And I'm going to put the metal in the center, and then I'm going to just highlight the B, which is the one that I'm going to focus on, and then this is a B on the neighboring side, and in the square planar structure, that's what we call the cis. And if you have a square planar, and the metal in the middle, and the B stands here, and another B on the opposite side, that's what we call the trans. And if you recall your Basper theory when you learn in the chemistry 1, this square planar structure is actually electron domain arrangement. The parent electron domain arrangement is actually octahedral. It's nothing different from the octahedral. And then this one is actually has a lone pair up and a lone pair down. So these are 2 lone pairs that you are not counting the define the shapes of or geometries of the molecule, but the number of coordination here is actually still 6, and that's why it's an octahedral structures. Second case is this. This is pretty obvious, and you look at that. Okay, there are 6 coordination. The one that before was 2 coordination, and 2 invisible lone pairs make up octahedral domain arrangement, but still the geometry of the molecule is a planar square. Whereas this one is plain and simple. This one is just nothing but octahedral. Okay, so an octahedral, and this is actually the same recurring theme that I talked about. Octahedral, draw the plane, just like that. And then you can put the metal in the center and another coordination on an axial position. Okay, so this is an octahedral. And then I'm going to focus on the cis trans where you're only involved. Try to pay attention to this B2, right? We're only talking about two domain arrangement, 2 ligand arrangement, whether they are in the opposite side. So probably this is a much easier opposite side, and then or they are on the same side. Okay, and so that's an example where you can find. Actually, if you look at the example here, they put an example of. So I will follow the same scheme, and they actually it's the same thing as long as they are on the opposite side from the metal, right? They are the opposite side of the metal. Or they are sort of the same side of the metal. This is a cis. This is a trans. So that's what we can find out. So this is a case where you have 2 identical ligands, And you need to look for their spatial arrangement to say the cis or trans. The thing that is unique about the inorganic chemistry, if you have an octahedral, and then if you have a three identical ligands, and then they can have some different kind of the geometrical arrangement. And I hope you guys can see this. I put a dotted line. This is a dotted line of the plane, right? And then there's things going up and down. And from here, it looks like they're the one faces of the pyramid, right? This is the one. Those three chlorines having on the same faces. So same faces, one faces, we call the FAC isomer. And if you look at the second one, it's the same, the compound with a triamine, aminino, and the trichloro, and the green is a chloro. They are forming a plane. Now this time, I'm connecting this, and connecting that, and connecting this. This is almost like going through it. It's not on the faces, going through just like going through the pole. And that's what we call the MER. It's coming from the meridian from that. And this is an FAC. So do it one more time. I can emphasize this one to you more when you see that three ligand and the arrangement of the three ligand. And you want to do that. And then this. So these are the two planar, and then there's an X. So those are how they are being arranged. And then I'm going to put the chlorine here. Let me put a different example. Okay, why don't I put chlorine here, chlorine here, chlorine here, right? So they form, the faces just looks like that. These are the FACmers, okay? So FAC isomer. And then if you have a chlorine here, and chlorine here, and choose anything over there, let me see, put the chlorine here, that's easier to see. Those planes, it's easier to put a little reference line, and those are the plane going through, and that's called the mer isomers. Okay, so once again, FAC versus meridian mer isomers is coming from metal with coordinate with three ligands. Okay, so the three ligands arrangement is the one that is going to be important characteristic, and because of this is a 6 coordination. And we call this is an octahedral, and that's why you are seeing these two different types of the isomers. Okay. Okay. So I think that I can put an extra mileage on this linkage isomerism. This is going a little bit overboard, but let me just give an example on this. And this linkage isomer is another isomer because the ligand can have two different types of lone pairs. And the example here is shown up. It looks like a nitrogen is kind of pushing the electron, lone pair electron docking. Nitrogen is at the head, the docking itself, giving the lone pairs to the central atom, or actually the oxygen atom has a lone pairs. They are the docking itself as the same molecule as a ligand, and they do have depending on which lone pair from which atom, nitrogen atom or the oxygen atom, they can call the nitro and nitrito. They are different. Okay. So NO2 is actually, if you draw the Lewis structures, it looks like this with a resonance structure. So like I said, either these lone pairs, that's a nitro, or this is a one. Oxygen lone pair from the oxygen, that there will be a nitrito, and that's the one. Another quite well-known example is this is what we call the cyanate with a thiol in it, and that's the one. If you write it in SCN, and then you need to draw the Lewis structures, and Lewis structure, because the sulfur is a cousins of the same column as an oxygen, so they are very similar to looks like an oxygen, and then to satisfy the octahedral and the valence electron, this is how it looks like in this thioisonate ion. And as you can see that this one can form the complex with the metal, right? This is a ligand. Or you can see that, oh, why don't I do this one other way? I just flip this molecule, right? And then you can see that this one is forming the complexes. So these are what is called the linkage isomers. And as people can show up which atoms are giving to the lone pairs to the central metal, and they can be different. So the whole idea is the most important concept that you should retain here is there's a metal always in the center, and then the ligand is trying to give out the lone pairs as a form, and sometimes there's more than one way they form this, what they call the linkage, right? What they call the linkage in the atoms. So this is the one. So okay, so I'm going to stop here now because I didn't talk about this d orbital energy splitting for the octahedral split versus tetrahedral. You can watch the YouTube video that I put it on in the part B from the another sections, and you can do that as well. And also I explained this concept in a different wording from the previous session, so you are welcome to look at that as well. So